Hello, I'm Jayateja, research scholar at IISc Bangalore, working with Professor Soma Biswas. Today, I am presenting my research work on robust feature learning and global variance-driven classifier alignment for long-tail class incremental learning. Incremental learning is a powerful concept that enables machine learning models to adapt and evolve continuously. The primary objective is to induce new information into model without forgetting the old knowledge. Consider a scenario where we initially have a dataset D0 consisting of three classes. The model trained on these classes is denoted as model 0, and this complete training process is referred as a task 0. As time progresses, two new classes are available for training, let's say denoted as D1. The essence of class incremental learning, training the unified model, model 1, using only the new data D1 and it have only access to the model 0, not to the old data D0. The goal is to learn model 1 that can be able to classify all the classes in D0 and D1. Here it is 5. This incremental learning process repeats as new classes are introduced. And this incremental learning becomes essential due to challenges such as data collection limitations, where we can't collect all classes data at once, and availability of old data. And again, it is a computationally expensive to train it from the scratch. Its applications extend to domains like robotics and autonomous vehicles. In traditional class incremental learning, we typically assume uniform data distributions at each incremental task. Means there is an equal number of samples for all classes in each incremental task. Here, the major challenge is catastrophic forgetting on old classes. However, real-world data often present in long-tail distributions, where different classes have different number of samples. The major challenge is the catastrophic forgetting on old classes and the underrepresentation of tail classes at each incremental step. So before discussing the proposed solution, this figure provides the performance on long-tail CIFAR-100 dataset. We compared our proposed approach with cross-entropy with the state-of-art learnable weight scaling approach. We conducted experiment on two different long-tail distributions, shuffled and ordered. In shuffled scenario, the number of samples in each class is random, and on the other hand, in ordered long-tail, the number of classes from first to last decreases linearly. The learnable weight scaling is a state-of-art two-stage approach where authors learn the feature extractor using traditional CIL approaches in stage 1, and in stage 2 they try to fine-tune this external learnable layer after classifiers using the balanced dataset. We observed a trade-off scenario as the performance on these tail classes increases by the cost of performance on long classes in both the settings. Fine-tuning classifier boundaries with balanced data tends to compromise the performance on long classes. In contrast, our proposed two-stage approach, GVLN aims to enhance the performance on tail classes without compromising on the long classes performance. This is possibly by integrating robust feature learning in stage 1 and classifier alignment with global variance in stage 2. Which means that at every task, the model will train through these two stages. The proposed approach can be treated as a module and that can be incorporated into any traditional CL approach in stage 1 to handle these long tail distributions in class incremental learning. Now I discuss individual block in detail. So the idea of classifier alignment with global variance is once the model trained on stage 1, its features and respective classifier prototypes are shown in the figure. Blue color line shows the classifier boundaries. Then we assign the global variance around the class prototype. It is like now boundaries are overlapped with class variance vicinities. And tune the classifiers. The red color line shows the classifier boundaries after alignment. Incorporating this not only preserves the performance on long classes but also enhance performance on tail classes. Now I discuss the complete approach GVLN. It basically involves the two stages. Initially, the model data has given and it contained the feature extractor f theta and classifier phi. The continuous data stream is denoted by d1, d2 till dt, and there is no overlap in the classes in d0, d1 and dt. In stage 1 robust feature learning, the model trained with the traditional CIL laws along with the mix-up laws to obtain robust features. So basically the mix-up loss involves a convex combination of two images and expect the model to predict the same mix ratio at the classifier outputs. So this simple incorporation of this robust feature learning resulted in performance gain across various tasks along different long-tail distributions. Once that stage 1 training is completed, the class prototypes are calculated for each class by computing the mean of their data points. These prototypes act as a class representatives for their respective classes. For global variance estimation, we propose to use the class with the largest number of samples during the base task. So, using tail classes for variance calculation can lead to inaccurate estimate and it failed to capture the class properties. So, using the class with largest number of samples for this variance calculation used as an informative measure that effectively captures the class properties, and it make it intuitive to align the classifiers based on this information. And empirically we observed this strategy significantly improves the performance on test data. The classifiers are tuned using the sample points from the global variance around these prototypes using a cross entropy loss. Here we denoted it as a LCA. From table we can observe that tuning the classifiers using the robust features and the global variance strategy improves different long tail tasks over various tasks in CIL. This slide shows the complete results on the various datasets over various settings. We can see that proposed approach outperforms all tasks across datasets. The figure illustrates the Voronoi class boundaries at task 1, where we are adding the 5 classes. The cross mark represents the world classifiers, and the star uh, denote the classifiers after the alignment. This blue line indicates the classifier boundaries before alignment, and red line illustrates the boundaries post alignment. This simple alignment enhances the performance from 43.6% to 50%. So in conclusion, our work tackles the long-tail class incremental learning challenges by incorporating robust feature learning and leveraging global variance as an informative measure to align classifiers. And thank you.